Hi. I'll start with my talk. I'm Johannes Bechberger. I'll be talking about building a lightning-fast firewall in Java and eBPF, and I'll be mostly talking about eBPF. I work at a well-known company called SAP, and I'm an OpenJDK developer, but more in the end. Consider we have a simple web application, and in my case, I work in OpenJDK, so I developed a small web page where you can see the JFI events, like profiling events. And consider now, this page gets popular. I don't know why, maybe first place in Hacker News, I don't know. And we have a problem. We get a DDoS attack, so too many users on the system, that's not great. Consider now that we've written the server in Java, also another language, but I'm choosing Java here because that's in the talk title. So what's the naive way of solving this is, the naive way is simple. You just have your web application, you have your web server, and essentially to block specific IP addresses, you just hook into the method that accepts your connections and is like, oh, should I block this IP address? Just looks it up in a hash map, and that's fine, and it blocks it. The only problem is that, where are we blocking? So the incoming packages go through the physical network into your network code, and then up your TCP/IP stack, up into your sockets, whatever, and then up into your Java network stack, and then to your application, and then you're there and saying, oh, I actually don't want this packet anymore. And that sounds kind of wasteful, because we're like checking these packages just at the last point where we could even check them, and it probably used up some memory, some CPU time, and that's not great. So the alternative is we use a firewall, and we could simply implement a firewall. Kind of implement a firewall here. We just call IP tables, because why not call it in Java? We could have written bash, but I'm a Java programmer, so we called bash in Java. Anyway, and we could do this, but how can we add more logic and improve the speed at the same time? Because that doesn't look that nice, if I'm honest. And if we add new rules with just calling IP tables, we probably could have written some nice Java APIs around it, but we won't do this here. If you look at the graphics, essentially that's from Cloudflare that benchmarked this in 2018 with a moderately sized system. So what they got was, like, with the IP table stuff, they dropped like 1.8 million packets per second in a simulated DDoS attack, and that was quite fine. That's far better than, like, as you see here, dropping it in the application, where you probably get like in a few 100,000 drop packages per second if you're lucky. But you saw in the keynote earlier this day that you want to become a rockstar developer, and so we want to become a 10x firewall, because everyone is a 10x developer now, but no one has a 10x firewall. So the idea is, you probably guess that this graph goes a little bit on the x-axis, go a little bit further, and if we look further, we see this. We see we can get some speedups, and some hefty speedups, some almost 10 times speed up, or 10 times more packages dropped. So with a moderately sized system, we can drop like 10 million packages per second. Keep in mind that, like, a package is around a kilobyte sized, at least, like with the normal IP packages we have. So you're quite literally saturating a 10 gigabit input stream here, and that's pretty awesome. So we can drop packages at a rate at which they're coming in, so have almost no overhead, which is nice. So if someone saturates your incoming connection, he can't send you more packages, because otherwise your whole system, like, is blocked. So the question is, what's the difference between? So down here you see IP tables. That's still, as we saw, pretty fast compared to drawing it in the application, but there's XDP, and that stands for Extensible Data Plane. And the idea is simply that we drop it far, far earlier. And we can do this even faster if we're offloading. So modern network cards that you have in, like, large servers, they have the ability to offload all the blocking onto a network card. So it's off your CPU, which is pretty awesome, because your CPU doesn't have to do anything. So the idea is here that we get as close to the physical network as possible and drop them there. And the main issue is why we want to do this is that allocations are pretty expensive. And so when the network package first comes into your hardware, then it's picked up once, it's copied from your hardware's memory, from the network card memory into the kernel memory once, and that's fine. We need one allocation because we can't directly properly access the network card's memory. But then there's after it enters into your network stack, there's another allocations. And allocations are terrible. And I'm saying this as someone who works with Java, but we do this all the time. But allocations are terrible when you're working with performance-critical code, and so that's the issue here. And the idea is we have essentially two options on how to drop it that early. We can either change the kernel, which is probably a good idea because we all want to be kernel developers, or we could add a kernel module. The only problem is API stability. So to quote Greg Hartman, who wrote an article on this topic, he wrote, "You think you want a stable kernel interface, but you really do not, and you don't even know it." And he's kind of right, and in his article, I'll link it later, you can easily find out why. The main issue is that he points out that, for example, for the USB interface, they changed it 3 times with every new USB version. They had to change it, so the kernel is inherently unstable. And that's okay because you just want to have the fastest kernel, but it's not that great when you're developing applications for it. So traditional ways, we probably won't do it because we don't want to maintain this. So what about a third option? A third option is already in the title of this talk. It's eBPF. It's a B because it's eBPF. Anyway, it's well nice to even have a children's book on it, so it's pretty accessible and doesn't waste your Sundays because you're fixing bugs. Anyway, so the idea with eBPF is that you essentially say, oh, we essentially are only interested in like a subset of the functionality of the kernel, only want to modify a subset of it. And it's enough, for example, for network packages to say, oh, I want to drop this package or want to pass it and want to have some small code there. And the idea is here that we write this code in a language because we need to, and that's compiled and down, and this whole runtime system is called eBPF. So the idea is that eBPF is making the Linux kernel programmable at native execution speed, and that's pretty awesome. You can essentially hook it in like you do with your UI frameworks, where you're like, when this button is clicked, execute this code, and yeah, that's the same thing what we're doing here. When this package comes in, execute this hook. Just that it all runs in the kernel, which has its own struggles. To quote Brendan Gregg, who is one of the main proponents for the technology, and he's also best known for shouting at hard drives in a data center. If you want to find it out, the link is below. And he sometimes like this when he's more sincere. He wrote, eBPF is a crazy technology. It's like putting JavaScript in the kernel. Don't feel put off by the term JavaScript. I think he meant it as a compliment. The idea of the whole eBPF runtime is essentially that you take your source code and you write it in some language that you like, for language that has a framework on this, and you then compile it because you compile down to bytecode like you do with .NET, like you do with Java, and this eBPF program is then transferred into the Linux kernel. Of course, you need root privileges because you're modifying kind of the kernel behavior, so you need special privileges, but essentially you pull it into the kernel, and in this kernel, there's a VM like your .NET runtime, like your Java runtime, that executes this. The only problem is, does anyone see a problem with like running arbitrary code in your kernel, even if it's trusted? Any problems? Any problems with like out-of-bounds exceptions? In the kernel, it's probably not a problem. It probably didn't hold like all air traffic for like a whole day in the recent weeks. It's probably not a problem. So anyway, they thought about this. So they have a verifier, and the idea of the verifier is essentially simple. You take your program, that's written in like a high-level language, you compile down, and the verifier is like, oh, you really want to check this pointer, and it checks, for example, when a pointer could be null, like, oh, you checked it, that it is surely not null, and it prevents you from doing out-of-bounds exceptions, and it even ensures that your program terminates, because you don't want to have a program that in kernel that accidentally doesn't terminate, because then your system is broken. For those computer scientists in the room, the room is not full, but maybe there's one or two there. Of course, usually for Turing-complete languages, it's not possible to prove any sufficiently complicated property, let alone that the program terminates. It's called the halting problem in computer science. But the idea is that verifier restricts the code that we can run so drastically that it's pretty easy to prove. Not pretty easy, but it's like simple enough. So the idea is essentially that we disallow things like unbounded loops, because unbounded loops are a recipe for disaster. They can be unbounded, as the name suggests. And also, it prevents recursion from being too deep. So sadly, no Haskell program in kernel. That's not, but who programs Haskell? I don't know, but you can't do this in kernel because your recursion can only be like 31 steps down. The interesting thing is the more eBPF is used, the more kernel developers improve the verifier and ensure that you can do more. So in the beginning, you could have only like executed 4,000 program instructions, which isn't that much, but nowadays it's like at 1 million, so it increases ever more. And the idea is then, when it's verified, you can be pretty sure that the program isn't like crashing your whole kernel, except you can probably still write eBPF code that does this. So they recently found bugs where it's like, when you put certain constants in the code and then multiply it, you can still have bugs, but that's another issue. Be in mind that you don't want to have anyone that you don't trust run eBPF code in your kernel, because it can do interesting stuff. We see it later. So, but then we have this bytecode. We could just run it in a loop. You probably, if you saw the keynote this morning, you can run it like in a simple interpreter like the esoteric languages, but that's pretty slow. So what we have in the kernel is actually a JIT compiler, and we have this compiler that compiles it down to native code. It's for all major platforms that people use daily, like x86, ARM, and S390. For those of you who want to work with mainframes, that's really cool. And they also get this enforced. And what you then take, you take this program, then it's verified, it's compiled, and then it's attached to a syscall, for example. And you can attach it to different things like network interfaces. But essentially, the idea is whenever an event happens, this is called. And that's pretty cool, in my opinion. It means your kernel gets to be scriptable. And the main advantage here is that, for one, it has safety advantages, because we're verifying the whole thing before we're running it, so no CrowdStrike issues. Then on the end, then we can ensure continuous delivery, because we can like continuous deploy it. If we every time have to run a new kernel, we can't do this, but we can, after a program is already running, and I show you in a minute how this works, is running, we can continuously update our programs, and it's also pretty cool for development. And then it's efficient because we have a JIT compiler in there, so it's pretty cool. I'm a compiler engineer working on the OpenJK team at SAP, so I'm always happy when someone uses a JIT. And it's standardized, so it's not something, it's like standardized, it's stable, so you can, with some modern techniques, you can even run it on like you can run a program that you wrote for a newer kernel, you can run it on older machines or the other way around, and that's pretty awesome. But the main problem that we have here, you saw before that we can attach hooks and everything, but it's really pointless if the hooks can't share data with our main processes here, with our userland process, because we want to get data in and out. And commonly, when we have normal programs, and you probably are right, there are two options to share data between two processes, because in effect, these are two separate programs. We have a userland program and we have a kernel-land program. And typically what we do, we either use socket, so essentially program A says to program B, hey, here's a message, and program B can take it asynchronously, which is pretty nice on one hand, because yeah, it's asynchronously. It's program A doesn't have to wait till program E runs, but it's probably not that efficient. And the more efficient way is by shared memory. The idea is that both processes share some memory, and they set and get from it, and you have to do some synchronization work. But any ideas why both approaches aren't really good in kernel? Any ideas here? Why we don't want to have it as a communication between like a userland process and something that runs in kernel? Yes, it's all about isolation. The main problem is we want the kernel wants to really control what's happening with the communication, because consider someone put someone put some bogus stuff in there. It shouldn't crash our kernel, and the kernel wants to control what you put in and want to do things like bounce checks, because we saw before the verify is really an important part of this whole endeavor. And when we just access some random memory, the verifier can't do anything. But with these APIs, the verifier knows, oh, this data structure should behave this way. You can put these put this large elements in there in your data structure, and so that's pretty cool. And so that's something that the kernel provides us with. And it's called a BPF map, and it uses this calls to communicate. So the main idea is that you have like processes there, and they then use system calls itself, of course, to communicate with these maps. And the eBPF programs, they can use maps to hold state too. And even I find this kind of interesting, some parts of the eBPF programs are itself maps. So when you have, for example, global variables, they're implicitly part of a map. That makes it interesting because you can query all state. So there are multiple different maps. There, for example, there are hash tables, simple as you know from all the languages you like JavaScript and PHP. You have arrays, you have pair-friend ring buffers. A ring buffer is essentially a circular buffer, like a bounded buffer, where you can write data on one end in and read data on another point. And the idea is that you can do something like asynchronous communication with it, because you, for example, when you log from an eBPF program, you log something in the ring buffer, your userland program can then asynchronously get the data, and that's pretty decent. Then you have the whole thing of least recently used maps, and that's pretty cool because you can essentially have maps that are implemented in a way that when the map is full, it doesn't fail, but the oldest entry is removed. And then you also have stack trace maps and queue and everything. And they're every day I think they're like they adding like every day a few of these, so it's growing and growing and growing, and the space is really active here. You should definitely follow it. So the idea then with networking is that, as we see here, you can hook at every part of the networking journey. You saw before that we can hook at the XTP part, so we can hook at like almost as close as you can as the hardware level, even offload it to the hardware. Then we can hook it at like the TCP IP level, and even like at the sockets level, so the top end of your network stack, and then of course at syscall and other levels. And that's pretty awesome because it allows you to choose what you want. So the more up you get in the network stack, the more information you get, and the more pre-processed the data is. But it's also less performant. And it's the other way around, because consider when a packet leaves your application, you also want to drop it as fast as possible. So you probably want to drop it at the top of the network stack, and that's pretty cool. So there are so many use cases. I can't count it here because in the last few years, it started like in 2016, but nowadays it exploded. The cool thing is for eBPF, almost everything is visible. So you have cross-system visibility of almost everything, of all the sockets, of all the volumes, of all the data, and that's pretty cool because it allows you, for example, to do cross-language profiling, because you have a profile that can deal with like Java processes with Go processes at the same time and sees all of them on the system. And that's really what many people use it for. They use it for observability and for monitoring, but they also use it for security control, because you can hook into different hooks from the Linux security module, and you can essentially prevent file accesses and other things. And the cool thing is, because you can hook it and write it and write these programs properly, you can extend it without relying on the kernel calling all the time back to your application, which is pretty slow. We don't like slow because it's usually commonly used on server platforms where performance really matters. And I mentioned it before, you can, for example, what CrowdStrike did, if I remember correctly, they had their kernel module in Windows, and that was not a good idea. And then they had, I think the issue was, what the layer found out was like an out-of-bounds access. And the cool thing is with eBPF, the verifier reminds you that, hey, you didn't check like the bounds, and that's very cool, so you don't have these issues. And currently at Microsoft, apparently regarding to some news sources, they are trying to get eBPF in, which is pretty nice. They already approached us there, and I think eBPF will grow. Not on the Mac system. You're seeing here them running a Mac. They have different systems, but on Windows and Linux, it's pretty hard these days. But of course, eBPF has bugs too. So you all write software, hopefully, but you probably know that your software has bugs. As good as you test it, you will always have bugs, and you find like 10 of these in the official CVE databases. And they are mostly related to the verifier, because when the verifier fails and the verifier can't find an issue in the code, then it can run and can crash your system. That's not great, but remember, you should only run eBPF programs from sources that you trust, because they run with kernel privileges. Let's consider the eBPF ecosystem after I told you how great it all is. You have on the lower level, you have the Linux kernel, nothing fancy here. I told you already, with the verifier, the JIT, and some APIs that help you develop it. Then you have on top, you have the user space, but you usually don't use just the system call and be like, fine, because that's really hard. So there are libraries for many languages like Go, C++, and Rust. And then on top there are like frameworks that like end users use, like Cilium, Falcon, something, and other profiles there. And anything missing here in this runtime? Any language missing here? It was a trick question. Anyone? Which language? Yes, Java. So of course there's Java missing, and so I thought about doing some eBPF last year, and I was like, oh, there's no Java library for this. And that's not good, because I work at Submachine, we're like the third biggest contributor to the JK. I work on like Java profiling, and it's cool. Yes, I thought, maybe let's change that. And you know, when you're like going into the state of hubris and be like, how hard could it be? And like 8 months later, I'm here. And it's the first presentation at a conference that I'll be giving at the topic. Oh gosh. And you know the point where I'm like, what have I done? How did I end up here? And that's the point where I'm here. So I hope you like this all, because I like Java kind of. Yes, I know it's many of you develop .NET, but still Java is the OG good language. And .NET came later. Anyway, to again quote Brandon Eck, eBPF is a crazy technology. It's like putting JavaScript in the Linux kernel, but you know what's also related to JavaScript? Java. No, I'm kidding. I was once at a conference where someone didn't know what I was doing, so she introduced me as a JavaScript developer, and it was like, no. It was really terrible. I don't have anything against JavaScript, but I think a language that's run like two days is probably not the best language to power everything, and you should definitely not run it in the kernel. I much rather write Rockstar in the kernel than JavaScript. Anyway, there's no JavaScript runtime in the kernel yet, but if you have any free time and enough beers, probably you start one yourself. How wrong could it be? Anyway, For all of you for the older people here in the room, you might have seen this reference, that I want to use a programming language which doesn't only run on userland. That's from a trailer of Java, so I can really recommend it. My idea was like Java is one of the most used languages nowadays. So you use it on server sides, mostly uses also for like Android to develop mobile apps, but it doesn't have any integration with eBPF. Isn't this like not good? I don't know, but it started working, and that's the result. It's Hello eBPF. It's the first and only Java library for eBPF. You can check it out. For all of you, I have the resources at the end as a QR code, so you don't have to scan all the resources now. And it's a work of progress. I worked on it for like 8 months now. I do this like as a Friday evening project at work, and then spend too many weekends on it. But you know, German winters can be cold and summers can be hot, so you know how it goes. It's a nice time there, and I worked on firewalls because finally I finished this demo this morning. But anyway, that's how it goes. It's the idea that now I show you how like a broad demo works, so that you can see that you can actually write the lightning fast firewall directly in Java, and then I'll later show you the building blocks. So that's the part where it's getting like to a demo. So wish me luck. Let's start this thing. I've written it with Spring. I don't know whether you know Spring. It's like one of the most used web frameworks out there in the Java world. And I used it and it hopefully works. Let's see. So there it is. I just make it a bit larger. So the idea is with this that when we have an eBPF library for Java, we can integrate it directly in your Java libraries, like you can do it with Spring or can use other libraries. And the cool thing here is that we can, in the kernel side, we have a rule, and the rule is pretty simple. You can define a rule by, hey, saying, oh, this is the IP address of an incoming packet. Please ignore like these many low bytes, just so you can say, oh, please essentially just catch all IP addresses. Then you can write the source port. For example, we want to drop every package that comes in from the HTTPS port, and we don't care about the destination port. So we don't care about the port that's like coming in on our system. Cool thing is when we now press send JSON, it hopefully works. And it hopefully works. And it hopefully works. When we now run JSON, then that's the problem with live demos. Just assume that it works. Okay, I restart the thing. So the cool thing is, so one of the problems when you ever do this kind of development, this happened quite often, is that LimaVM, which I'm using to run this on my Mac because Macs are far easier for presentations, it sometimes just stops working. And so I just restart it. And the cool thing with this library while starts, I can tell you about, is that you can quite easily integrate it. You can quite easily integrate it into application. Okay, gosh. I'll start some more information. So what we're doing then after we start is we're doing some live coding, so you see how you can actually write some simple programs that run in the kernel. And of course, you have to run it via sudo because you're modifying the kernel. And the thing is, what it does in the beginning, it starts your Spring application, but it also starts up the firewall. So what my application does, it does all the bytecode compiling at build time. So it's usually pretty fast to build up, but what you see when you develop some eBPF applications, it takes the kernel some seconds to actually do the verification because it does quite a lot of work. But apparently it worked now, so we can send a JSON. It worked, thank God. And the idea is this object is directly put into the kernel. Think what you want about putting things from the network unchecked directly in the kernel, but it's put in the kernel. The kernel does its thing, and then when we trigger a request on the server, for example, we let the server request a web page, HTTP web page, it's blocked, and we should in a second see here that it's blocked. And you should see appear things here. Probably, you know, JavaScript development is hard, but you see here that we're opening, but we don't getting anything back. And now we're going to the live coding part. I would call it having fun with eBPF, and we still have like 15, 20 minutes left. So that's what we're doing now. So for a simple hello world, I hope you can see. Can you all see it? Cool. For a simple hello world, it's pretty simple with Malari. You just tell it at BPF. Just tell it, hey, that's a BPF application. By the way, you usually want to give it a license because the Linux kernel is GPL licensed, and only some parts can be accessed with non-GPL code. So you tell it which license you have here. You also tell it, like, hey, that's a BPF program. That's fine. And what we also want to do, in this case, we want to get hooked, add a hook whenever a file is open. So we use the system call hooks that we have here. Now we can now just implement something. For example, we can use the openadd method, openadd2, that's used by many programs like cat or anything to work. And it's an interface, so we have to write implement. So the cool thing is that's called whenever file is open. So whenever a system uses this, and for example, what we can do, we can just use bpf trace print k. That's kind of the printf debugging that we usually do in some languages. And what we can do here, we can just print the file name, which is opening. We can just say opening the file name. And what we then have to do, we have to, of course, attach it somewhere. So we write our main method. If you don't know Java, you always need like a public say main method. But the cool thing is we can just say, we can just get our program and load it. So let's load the program, sample that class. And what we, of course, have to do, we have to attach it. So we can tell, please attach me everything you know how to do it. And then just say, hey, please print. And the cool thing here is that the part here, this runs in the kernel. That's compiled down to C. Show you soon how it works. But this runs in kernel, this runs in userland, and they communicate seamlessly. So let's try it out. We just have to use Maven. It's like in Java world, it's like one of the most used build systems. And this then runs it and compiles it down. And when we load it here, it's loaded in the kernel, and you don't have to do anything. So let's see how it works. And now it's pretty simple. We just use our run script. It just runs it directly. And you see here, these are all the files that are opened. These are all the files that are open on your system. And the cool thing is that actually, you see here, it's the same string that actually runs in the kernel. And I find it pretty awesome because you can even do more things. So an interesting thing with this is you can do nasty things with it. So we all want to do interesting parts, I believe. What you can do with this is file name is essentially in the C code that we have is essentially just a pointer, and it's a pointer in user space. So does anyone have an idea what we could do interesting stuff with? Could we modify it? Anyone wants to modify this thing to hide some files? So yeah, that's essentially what we can do. And it also shows here the power of like eBPF. So what we have a method that's pretty simple. It's called isFileForbidden. That also is compiled down. It runs in the kernel. That just checks, is this the file /tmb/forbidden? You see here we need to have bounded loops because we want it to terminate. But how enter open-end now works is we first read, because it's in user space memory, we first have to read the file name, and then we check, how is this file forbidden? And if yes, what we do, we write user space, because we cannot only like read user space memory, but we can write it too. So what we do, we just write the empty string in, which is pretty nice because we essentially hiding this file from access with this. So I can show you how this works. So we have the demo forbidden file here, and what I now do is I open a different shell so we can just see. So what we can do here, we can try to touch the file. Let's see. You see the issue? It's like down there. It tells us cannot touch the empty file name. Yes, because we modified it. And the cool thing is that runs all in kernel and then modifies it, and that essentially hides it. Of course, we can do things with symbolic links and everything to like to work around this. But the cool thing is we can easily like hide it from the obvious onlooker. I think that's pretty interesting. So be aware that people can do bad things with eBPF, but this could also help to, for example, hide files that you don't want others to see. So, yes. And why didn't I do this before with like the BPF transparent K? Because these helper methods, they are special. They do magic things. But the main problem is this points into user space, but we're currently in kernel space. So essentially the idea is that we tell our kernel, please read this piece of this string, and the string has a certain size. We specified it here. Please copy the string in from the user space. And the same thing is when we're in kernels, when we want to read kernel memory. We cannot directly access it, and that's for good reasons, because the kernel can do tricks, and also the verifier knows of the behavior of this. If you just had a mem copy, that wouldn't be that easy. So that's the whole thing. That code is in user space. That memory, we have to read it directly. And that's like one of the problems when you're like at the boundary between user land and kernel land, and when your system call is like in between, so it runs in the kernel space, the implementation, but it gets all its arguments from the user land. Any more questions? Good. And that's the cool thing. We can just write simple programs here. You're allowed to do a subset of Java. You're allowed to do loops. You're allowed to do strings. And that makes it pretty easy to try things out. Now back to XTP. The idea, as we saw before, is that XTP essentially allows us to hook into the network card, like at the bottom of your network stack, and check whether packages parse or should be dropped. So essentially, your packet comes in from the internet, goes like at the start of your network driver infrastructure, and then it asks like, hey, eBPF program, should I let it parse or should I let it drop? And if it should parse, then it gets further through the network stack. And to your applications. And the cool thing is that your eBPF program can communicate in two ways. So you can get data from your, in my case, Java eBPF application. For example, it can set the block IPs. As we've seen before, you can set the rules. And you can send back information like statistics and other information. And that's pretty cool because it allows us to build versatile applications with this. Important here is that you learn a lot about things like kernel, because you quite literally sometimes have to look in the kernel how things are implemented. But also you learn a lot about, here in this case, about how networks packages work. Because what XTP gives you, and I show you in a minute, it just gives you, hey, here's a memory space. Here's like the memory space where this package lies. I don't know whether it's a TCP packet because I don't care that the process hasn't processed it yet. So your Linux doesn't know, oh, is it an IPv4, is it an IPv6? It just knows that's an Ethernet package of like size 1 kilobyte. So just a little heads up for you, that's how packages look like. So a package on the network first has some Ethernet information. And from the Ethernet information, from the Ethernet headers, you get, for example, information, is this an IPv4 or IPv6 package? Then your IPv4 package knows the protocol, like is it TCP, UDP or more, and has some addresses, like your incoming and your external IP addresses. And then there's the TCP layer. Essentially, it contains the ports and it wraps like the HTTP packets. And now we're here again, and the cool thing is how do we implement this? It's pretty simple. There's an interface for this. It's called XCP hook, and so what you can just do is there's an XCP handle packet, and it's like with every handler that you've written before, you get some information in. What do you see here? And that's Java code that it generated to back the Linux code is, you can see here that we get data on the data end, and we can also get the network interfaces that the package is incoming and outgoing, which is pretty neat to know. You know then, oh, is it coming via your internal devices, or is it coming via the Wi-Fi? But essentially, we have the packet, and a pretty easy way would be we just return enum. We could drop everything, but dropping every package is not that great because we essentially block any communication with the system. But what we can easily do, we can use global variables. And for example, what we can do here is we can create a global variable that's an unsigned integer. And we can call it count. And you probably can all guess what this does. Every time we get a package in, we say count is the count plus 1. That's simple to write. The cool thing is here that we can then say, oh, by the way, if count.getMolar3, for example, to drop every third package is like 0, then we just drop the package, else we'll let it parse. And that's a simple, it's not a firewall because it just randomly drops every third package, but that's code that actually drops your packages at high speed, every third of them, every third incoming, and that's pretty cool. To attach it here, we have to attach it to our network interfaces. And the cool thing is here, you see here that we have a global variable. How cool would it be if we could just read a global variable from the user land? And we can. So for example, we can just every like 500 milliseconds, we can just print this. So counted, and we can just access it as before. We can use, in most cases, like the similar methods that we used in eBPF, but and that's Java, so we have checked exceptions. And that's all. That drops every third package coming into your system. Let's give it a spin and hope I coded it correctly. And you see sometimes, yes, it has to be final because my code would be terribly confused if you reassign count, because under the hood, it's quite some effort to make it working. And you see here how to integrate an application that's written in Java with eBPF code. And that should now work. So good. And now we're running it. And then counts packages, and every third is dropped. You see here, like everything that happens. And when we, for example, when we get the Google homepage, the count increases. And I can tell you web servers don't like it if you drop every third package, because it also means like acknowledgements and TCP level are dropped. But the cool thing is, using this and also doing similar stuff with files, you can easily test your application whether it's really works. For example, whether it works when your network connection is really horrible. And that's pretty cool. And you can even, like, if you want to do it, you can even extend this to implement more complex stuff. For example, you could do here pseudo random number generator that just like pseudo randomly drops these packages, and that's, I think, pretty awesome. And to quote Clark third law, any sufficiently advanced technology is indistinguishably from magic. And I think when you see this, I feel it sometimes like I can run Java code in the kernel. How cool and sometimes mad it is. And the cool thing is with Java, how I got to there is that Java in like the recent versions got Project Panama, which essentially allows us to easily interact with native libraries and to easily allocate memory and to easily interact with libraries within C and C++. And this is the thing that makes it possible, because in the end, I'm relying on the eBPF, I'm relying on the well-designed library under the hood. And how it works technically, so for all the people that want to know here, is that essentially we take our program, we've seen this program before. In this case, we have a method should drop, because you can, of course, as we've seen before, define methods. And it's first then preprocessed, and all the data structures are resolved. And then I take the abstract syntax tree and then transform it to C code and then compile it down. And the eBPF code for something like a should drop that just checks whether the count modulo 3 is 1. That's how it looks like. It's not hard. It's a pretty simple machine, but it's powerful enough to write proper programs. And the cool thing is it's close enough to modern machines that you can easily compile down. And if you're interested in more, I'm writing a blog post every other week since January. You can follow the whole journey, all the things that were hard documented there. I wrote the last blog post yesterday on the train here from my hometown of Karlsruhe to Copenhagen. So I can definitely, so there you find more information on how the firewall is implemented. And I want to say thank you to my team here, because I work at Submachine and they allow me to do this here and to present you how cool stuff you can do with Java, especially with the modern versions. And as a glimpse into the future, I hope that Java will become a first-class language for this, at least for like demo applications as we've seen here, so that also non-Go and non-Rust developers can enjoy working on eBPF. And maybe someone wants to do this for every language, for any other language, which is cool. And essentially what we're doing, we're moving towards a microkernel with this whole thing. So we're putting functionality out of the kernel and letting users write them kind of externally and just attach it. And that's pretty cool, because we can then modify the kernels to suit what we want to do. For example, Facebook uses eBPF and uses the XTP stuff to do the load balancing, because it's far easier than implement kernel modules. And the cool thing is also we can do kernel fixes and fixes for other stuff here. And hopefully, fingers crossed, sometime in the future we can even write schedulers in eBPF. There's currently a project called ZX, and they're trying to get it in. So you can write your own schedulers in Java. If you're interested in more, you can come to my talk, and you can visit my talk at the eBPF Summit in 2 weeks. It's an online talk where I tell you all about this, and I hope it works, because it's really cool. You can do so much things with eBPF. We're looking forward. So it was a great experience developing this. I can tell you, developing, trying to write essentially C code in Java is interesting, but also because with these projects, you learn so much, not only about technology, but also about yourself. Because I struggled so much getting this working, because in the beginning, I didn't know anything about eBPF. And you can follow this in my blog post. I started this to learn eBPF. And that's why the project is called Hello eBPF. It's like, hello eBPF, hello Java. I don't know what I'm doing when I'm doing this anyway. I'm glad to be able to present it here. And I want to say thank you to of course, my team. It wasn't possible without them. Also to Dylan Reimer, he's a really nice guy who is like, when you're like asking Google, I instead ask Dylan Reimer, it's faster and the responses are much more accurate. It's like my ChatGPT version, just the responses are like short and good. And doesn't hallucinate that much. Anyway, when you want to read about the resources, watch the videos that are referenced. Just go to this link or see someone shouting at hard drive to check monitoring applications. You can find myself on my blog, Mostly Notice, where you probably see a blog post like every 2 weeks. So the next is coming out next week on how to write a scheduler. Let's see whether it works. It's always work in progress. You can follow me on Twitter or on Mastodon. And if you have any questions, we probably have like a few minutes left. And after this, I'm here at the conference. You can just ask me. And if you want stickers of my cool team, just pick them here in front. And thank you for your patience and for coming with me on this journey to see how we can actually use Java to write stuff in the kernel. Any questions? Far better. So the thing is, that's currently a research project. I'm currently at a level where it's like a proof of concept where I can show you demo applications and where you could write simple programs in it. But of course, behind the Go and Rust implement, there are large companies. There are multiple people, not just me. So I would hope that in a future time, the Java library would be on par. But of course, it's in its early steps, but it has many cool and interesting features that make it easy to write eBPF applications. Of course, it has still bugs, but I'm working on it. I'm spending too much time on it to fixing this. So I think it's good for getting to know eBPF, and then if you want to do more serious projects, then you probably gained enough knowledge that it's quite easy to move over to like the Go library or to the Rust library, because the APIs aren't that dissimilar. So it's a good thing to try it out because it's easy. You just have to download it and it should hopefully work here. But of course, don't use this in production. Any other questions? So the question was, what's the state with Windows? Because I mentioned it, so there's limited support as far as I understand for running eBPF there, but it's currently an ongoing effort. So it's currently totally in flux, but I would expect, like, I don't know, probably next year so to see some announcement. There were already announcement of like preliminary features, and if you want to follow this, there's the eBPF newsletter that I can really recommend. Just go to eBPF.io and register. And yesterday there came something out about like using it on Windows. So just look there. It's in its early steps, of course, because this was designed for Linux, and still on Linux they're adding so many more features. But I think you should definitely follow this space because it will get bigger in the next following years, especially after CrowdStrike, which like probably burned some people hard. So yes. The question is essentially regarding the attack surface. Of course, there's an argument, and is to quote a kernel developer, he was like, "Oh, you're essentially opening Pandora's box." Yes, you're doing, but the alternative is that everyone runs Linux kernel modules. And that's far worse, because you don't have any checks on, you write this in C++, which is like interesting regarding memory safety. So yes, it opens Pandora's box, but we see so many benefits. We see it for DDoS protection, for load balancing, for security. So I think the potential outweighs the risks.
So you mentioned that macOS is going a different route. What is BSD macOS doing, or
I'm, if I'm honest, I'm using a Mac, but I don't know that much. But I think they have different ways to do all the security stuff. And it's important to note that, like most performance-critical systems, they don't run on Mac systems. So usually, also when I'm focusing on profiling, I'm focusing on server systems, and they usually just run Linux. So load balancing on a Mac system doesn't make that much sense. So there are other mechanisms there, but if I'm honest, I don't know. If you find anything out, send it to me. I'm always happy for new knowledge, as you probably are, because you're at this awesome conference. Yes.
and then the second question: what happens actually if this thing crashes? What happens if this thing raises an exception? Does it result in a private panic?
So there are two ways. So for example, for one, you have to verify that checks like, oh, everything is fine. So in the most common case, nothing should happen. And if it crashes, yes, it might. It might, of course, cause a kernel panic because it runs in the kernel. So if you see here, if we skip back at the beginning and have a minute time again. So if you look here, for example, there are other bad things that can happen if I just read out the CVE 500. A flaw was found in unrestricted eBPF usage with BPF BTF load, leading to a possible out-of-bounds memory write in the Linux kernel's BPF subsystem due to the way a user loads BTF. Like BTF is like type information. This flaw allows the user to crash or escalate the privileges on the system. Yes, on S390, a local attacker with special user privileges can circumvent the verifier and may lead to confidentiality problems. So yes, the problems exist. Don't use BPF from unknown sources. That's a terrible idea. And don't use it from people like me. Use on your production systems. There are engineers that are working on this and they know what they're doing. I like to play with it, but there are people that also testing this. Testing is hard, but you should definitely do it. It's with every system, it's with every, especially safety critical system. So don't just download it from the internet. And then also, when you're doing some test stuff, I'm running it for good reason in VMs. So try it this way. Don't try it on your mission critical system that powers, I don't know, nuclear submarines. Anyway, I think we're off with the time. I'm happy that I spoke in front of so many people. It's just 10, but that's good enough. Or 8. But anyway, if you have any more questions, just come over later after this talk, or reach me via LinkedIn and such. I'm happy to answer your questions, and maybe you try it out. And have a nice day, and have a nice conference. Thank you.